Hi everyone, this is Kostis Karantias, and today I will present to you proof of burn. This is joint work with Aggelos Kiayias from the University of Edinburgh and Dionysis Zindros from the University of Athens. So this talk is basically concerned with burning cryptocurrency. The kind of setup we have is we have Alice who wishes to burn some of her coins, and then after she does that, she wishes to convince Bob or some other party that her coins are actually burned. And for this, she provides him with some proof, and then he can verify that the coins are actually burned. So before we go on to define more formally what burning is, which is the main topic of this work, let's first talk about why would someone burn money and destroy it at all. So in cryptocurrencies, there are some use cases that have appeared in previous work. So one of them is Open Bazaar. Open Bazaar, for those of you who don't know, is a decentralized marketplace, and it has been around for a long time. Now, all stores in Open Bazaar are basically anyone can create their store. So it is kind of hard for users to trust stores because they could just disappear overnight. And so there's no guarantees at all, and there's no centralized entity to guarantee to you that you will not get scammed, for example. So a proof of burn is used for this in the following manner. So imagine you open a physical store, for example, then the reason people can trust it like implicitly is that it costs to set up the store, right? So you have this like whole building maybe, so it costs you to make this, and it's probably not worth it to you to just scam someone and then like tear it down and go away. So in the same sense, in Open Bazaar, you have vendors actually burning money to show this kind of commitment themselves, to show that they're actually not going to disappear overnight, and it's not worth it for them to scam you for like pennies, for example. So Open Bazaar made use of this, and in order to kind of imitate a trust, basically because they couldn't, they can have a centralized trust system like you can, for example, with eBay. Now, then another very popular use for proof of burn has been bootstrapping some new cryptocurrency, and I'm sure you're aware that new cryptocurrencies do all kinds of various things to provide new coins, but Counterparty basically was a pioneer in this, and they said you can get within some fixed time period, if you burn some of your Bitcoin, you will be able to get some Counterparty coins. So you basically burn Bitcoin and generate some other coin. So one important point I want to bring here is that actually proof of burn is not new. It has been around for a long time, I think since 2011, and it's been invented by Ian Stewart, who is at Imperial College London. So okay, so now let's start and see basically what our formalization looks like. So we have Alice, and she starts with some string, which we call a tag, and this can be any kind of string she selects. And then she uses this tag to generate a burn address. And then when she generates it, it just looks like a normal cryptocurrency address, and then she can just send coins to it. And then she will know that this money is basically destroyed. And if she sends the tag and this transaction to some other party, let's say Bob, then Bob can actually check the transaction and see, okay, Alice actually burned her coins with this tag, and basically Bob can be sure that these coins are basically unrecoverable. So let's dive into more the tag more. So the tag can be any string of the user's choice, as we said. And for Open Bazaar, for example, it could be the vendor ID. So if I am a vendor, the way I do the burn is I I take my vendor ID from OpenBazaar, and then I generate an address with that, and then burn some coins, and then publish the proof on OpenBazaar, for example. So now let's start looking more at our contributions to this. Now, this is a more formal definition of the protocol I just stated, which says basically that a burn protocol consists of two functions. One of these functions generates the burn address, and is called GenBurnAddr, which takes a security parameter and then the tag T, and it gives you the burn address. And then we have the burn verify, which Bob in our example should run, which also takes a security parameter. Then it takes the tag and some address, and then it verifies that this address is actually a burn address for that tag, and it actually encodes it correctly. And then we actually base this on a blockchain, an underlying blockchain protocol. And it turns out the only two things we need from blockchain are the address generation. So basically when you start a wallet, it generates some key pair for you. So you have a public and a secret key, and then from this secret key, from this public key, an address is derived. So this is what GenAddr does, and of course it's auto-deterministic. Every time you run it, it should give you like a different address. And we have spend verify, which takes a transaction M and then a signature, sigma, and a public key PK, and it basically verifies to you that, okay, this transaction M is spendable by PK. And this is what the GenAddr and spend verify look like for Bitcoin P2PKH. P2PKH stands for pay to public key hash. So you basically, when you send coins to someone, you send it to their public key hash instead of their full public key. And yeah, so this is what the verification looks like. You take a public key hash, and then you extract from the signature the public key. You verify that this public key matches, like if you hash it, it matches the public key hash that you were given, and then you verify that the transaction is signed with this public key. And the address generation is basically just relies on the underlying signature scheme, where you run the gen, and it gives you a public and secret key back. And then you hash the public key to get a public key hash, and then what is returned is basically the public key hash and the secret key. So now let's look at the properties of the burn protocol. And so we have correctness, unspendability, binding, and uncensorability, and we define this formally. So correctness basically says that if we have Alice and she burns and she does so according to the protocol, then Bob will have to be convinced that she actually burned. So this is a pretty basic condition. And then the main thing for burn, like turns out to be unspendability. So you basically, what is required is that if someone burns their coins, that they're not able to spend them in the future. So like this is the crux of proof of burn basically. And if someone actually tries to fake a burn, then this will be detectable. So this is like more formally how this is defined, and we define basically a game for this. So this is how spend attack works. We request from the adversary that they generate some tag and then an address and a transaction to go with it, such that the address is a burn address for the tag provided, and then also the transaction spent coins destined to that address. So if this happens, then the adversary wins the game. And what we say is that the protocol is unspendable if for all adversaries all adversaries succeed with at most negligible probability. Then binding says basically that the tag that is associated, there's only a single tag that can be associated with a burn. So basically, this is like a collision of burn address generation. It could be thought of in this way, in which only a burn address can be matched only to a single tag. And the game more formally is, so bind attack basically requests from the adversary that they return two tags and a burn address such that these tags are not the same, but they verify with the same address. And then, of course, the protocol is binding if this can only happen with negligible probability for all polynomial time adversaries. And then we have uncensorability, which basically we need to say that people who observe these transactions are not able to distinguish them as burn transactions. And there might be many reasons to do this. For example, one could imagine that miners of a cryptocurrency may not like that people burn, and they may think this would impact their usage of the chain they're mining on, and they could try to censor such burn transactions. So we think this is also an important property. So uncensorability is formally defined in the following way. We have two distribution ensembles. One of them is basically the address that would be normally generated by the blockchain protocol, and then the other is address generated by the burn protocol. And we define the uncensorability with respect to some distribution of tags T, and then we say, okay, the distribution of the burn addresses is as follows. We draw a tag from this distribution of tags, and then we generate a burn address for that tag, and then we return that address. And this is how this second distribution ensemble is produced. And then we require those two distribution ensembles to basically be indistinguishable. So now let's look at the next contribution, which is that we propose our own scheme for this. And it is actually a very simple scheme. So we have Alice, and she basically starts with some burn metadata, which we previously called the tag. And then she basically needs to hash this and flip the last bit. And we call this flipping a perturbation. So then this basically is what will be her address, and this is already like a Bitcoin address, for example. And then the proof of burn, for proving that she has burned, she can actually provide a transaction and then the tag and then someone else, because this is deterministic. If they follow the same procedure and go and hash the metadata and then flip the last bit, they should arrive at the address found in the transaction. And then if there's a match, they can accept the proof. And this is the more formal definition of a scheme. So as we said, German addr works by taking this tag T, it hashes it, produces this TH, and then TH prime is basically TH with XORing by the bit 1, which is basically flips the last bit, and then this is what we return. And then verification, because this is deterministic, we can just invoke German addr again on the tag and verify that the purported address provided, that and verification works as follows. So we basically take this tag and then we run German addr ourselves. And because this is deterministic, it should give us the same TH prime as provided. So actually in the paper, we prove that all the properties that we mentioned earlier, that they are covered. So this scheme is secure. So let's go through them very quickly one by one. So we have correctness, and I guess correctness may be obvious because burn address generation is deterministic, and that basically the prover and verifier, they run the exact same code. So verification should always pass for a German address. So unspendability is basically helped by the fact that we flip the last bit, and it is basically computationally infeasible to know the preimage of both some value A and then this same value but with the last bit flipped. And we actually prove this, we'll have a full proof for this in the paper by modeling the hash function as a random oracle. Then binding directly follows from the collision resistance of the hash function, because if someone produces two different T's that both verify for the same address, then it means they hash to the same thing essentially. So we also prove our scheme uncensorable, and in order to do this, we need to assume that the tag distribution is unpredictable. And so then basically the proof is based on the fact that the hash of an unpredictable tag and the hash of a public key, which from the signature secure signature scheme gen algorithm comes out also as an unpredictable value, that these two hashes are basically both look uniformly random. And we also utilize a random oracle in order to prove this. Now, so an interesting use case for this is to actually bootstrap a new cryptocurrency. So if we have an existing cryptocurrency, then we can basically burn coins there in order to mint them on the new cryptocurrency. And here we have a kind of pictorial representation of this, where on the top we have the existing cryptocurrency, and burn happens on that block that is marked as black, and then on some other block on the new cryptocurrency, which blockchain is shown below. We basically reference this burn in order to mint new coins, and then we can have a rule that says coins can only be minted if a corresponding burn has been made on the existing blockchain. So our final contribution is that we have implemented this on Ethereum. So it's basically a smart contract that mints new tokens if a corresponding burn on Bitcoin has been made. And the costs are as little as 28 cents per burn. Another thing I would like to touch on is that if any of you is familiar with Bitcoin, you will know that Bitcoin has a special opcode for in Bitcoin script, which is op-return. And basically, if you have an op-return in an output, this directly makes the output unspendable. And this actually kind of helps the network because full nodes in the network actually need to maintain the unspent transaction outputs or UTXO in order to be able to verify new blocks and transactions. And by burying using op-return, basically nothing is added to the UTXO because the outputs returned by op-return are by definition unspendable, so there is no need for them to be kept around. And in comparison, the kind of burns that we show with our construction, they actually will remain in the UTXO forever because exactly like miners have no way of knowing that they cannot be spent. So op-return is more efficient in that you don't pollute the UTXO, but the scheme is censorable. So if you have a burn with op-return, then this is directly visible and miners could censor it. Another problem with op-return is that it is not that usable. So the problem that you have with this is in most wallets, the functionality you have is one of sending funds to other addresses, and actually creating op-return outputs is not supported by any major wallets. So with our scheme, what you can do is you generate the burn address, and then you can actually send money to it from any wallet you might have. So that this actually gives it a huge advantage in usability. Now, another thing that could be done is to do a P2SH or pay-to-script hash script, which contains an op-return. Now, this, because the script is not revealed, this also pollutes the UTXO, but it is not generic. And we actually make a distinction when comparing all the schemes to actually focus on schemes that are generic that can be applied to multiple cryptocurrencies. So, for example, our construction can be directly applied to Ethereum, for example, or basically anything that uses public key hashes. And whereas P2SH, for example, is only applicable to Bitcoin-based cryptocurrencies. And so this is a full comparison. And so these are the properties basically for the comparison. We have binding, which is a property we saw before, but then also flexibility, which is how applicable the scheme is, and unspendability, uncensorability that we saw before, and then user friendliness, which basically says can a regular user use this? Can they use it with just a standard wallet? So from these, we have op-return, which we saw. We have P2SH op-return, which we also saw, but we also have nothing up my sleeve, which we didn't see. And nothing up my sleeve is basically I mean, probably the oldest trick used for burning. And how this works is you basically send funds to an address which is kind of obvious to everyone that you could not have the secret key to. For example, in Bitcoin, one may send funds to, and they actually have done so, like in incredible amounts, send funds to an address which is basically a hash of all zeros. And because of how likely it is for anyone to have the secret key to this, we consider funds there unspendable. And then finally, we have our own scheme, which here we say is AXO1. This is how we label it. So op return, like both kinds of op return are actually binding because the tag is directly in the output basically. Nothing up my sleeve is not binding because it's basically a constant address. And then our construction is binding as we showed. And then with regards to flexibility, nothing up my sleeve and our work can be easily adopted by other cryptocurrencies, for example, Ethereum. And people have also burned using nothing up my sleeve in Ethereum in the past, and there are also huge sums of money burned there. Now, unspendability, because it is like the crux of a burn, like a burn is not considered a burn if it is not unspendable. Like everything covers unspendability. Uncensorability, only the pure op return output does not cover it because, again, the output is directly reveals that it is unspendable, that is uncensorable. And then user friendliness, basically, the only problem is that wallets cannot return. You cannot generate op return transactions, but they can generate P2. They can send funds to P2SH addresses as usual. They can send funds to nothing up my sleeve addresses, and they can also send funds to our kind of addresses. They're all standard blockchain addresses, and they can be used in any way. So to conclude, in this work, we define proof of burn formally for the very first time, and we propose our own scheme, which is pretty simple, but we also prove it's secure in the random oracle model. And we show how proof of burn can be used for one-way pegs, even for cryptocurrencies with disjoint blockchains. And we provide the implementation of a Bitcoin to Ethereum one-way peg using this proof of burn, using our own proof of burn scheme. And we actually demonstrate that it is practical. So thank you very much for your attention, and we can now take questions.